Hello, Royals. For lesson 4.10 on 3D trig, I would like to do the diagrams with you and maybe take a look at some of the mathematics involved as well. So there's no special trick to doing 3D trig problems. You just need to split it up into two-dimensional trig problems. It is not required to draw a 3D sketch. Some students find it useful, some students find it very, very difficult. If you are having a hard time drawing 3D sketches, then I'm going to suggest you read through the problem and record horizontal and vertical information separately. Okay? So let me read through example 1 with you. And instead of doing the 3D sketch first, I'm going to do a top view and a side view. It says, from the point B, Manny uses a clinometer to determine the angle of elevation to the top of the cliff is 38 degrees. That right there, that angle of elevation, that's a vertical angle. So I'm going to draw. Here's the cliff. I think in my lesson I had A there and C there and B there. Probably should have used M for Manny. Okay. Here's the height of the cliff that I'm looking for, and the angle of elevation is 38 degrees. Well, in grade 10, we would have measured inaccessible heights by figuring out, well, how far from the cliff is he? Maybe Manny can't get to the cliff because there's a river in the way. Okay. Then it says, from point D, 68.5 meters away from Manny, Joe estimates the angle between the foot of the cliff himself and Manny to be 42 degrees. That's a horizontal angle. This is how far he's turning his head. So let me go to a top-down view. I'm seeing the foot of the cliff here, and here's point D, where Joe is, and here's point B where Manny is. So this is my top view, and this is my side view, and this is my top view. In my side view, you could think that like Joe is out, it's going to be hard to see with this camera, but he's out here coming out of the page. From this top view, you could imagine that the cliff, the point A, is like up here, again, coming out of the page. Let me put the information on here. Manny and Joe are 68.5 meters away. Let's see. Joe estimates the angle between the foot of the cliff himself and Manny to be 42 degrees. And Manny estimates the angle between the foot of the cliff himself and Joe to be 63 degrees. Okay. That's all the information that we have. We have enough information. We're trying to find the height of this cliff. We don't have enough information in this triangle to solve for the height of that cliff. We have enough information to solve this triangle. We could figure out every angle and every side. We don't need all of that information. And from your labeled diagram, what you're looking for, I guess if you're looking for a trick, our approach is to find a shared side, a side that belongs to both the side view and the top view. And this is where a 3D diagram might help you out a little bit. Okay. 3D diagrams, you generally need to draw in perspective. So here is the surface of the Earth. It is flat. This is me looking into the surface of the Earth. And here's the foot of the cliff right here. And the cliff is coming up out of the Earth. And there's the top of the cliff. I'm going to draw Manny over here. And what frustrates a couple of students when they're reading somebody else's solution is they say, I thought you said that ACB is a right angle. And it is, and it's very important that I label it as a right angle. But I hope you can understand how someone would be confused here, because that doesn't look like 90 degrees. But this is the idea of perspective. Here's a type of ruler that I have where this is a 90-degree angle. Well, what happens if I look at it on an angle instead of from above? Doesn't that look a little bit like 120 degrees to you? Just, I don't know, just take a corner of a piece of paper. There's a 90-degree angle right there. But if we look at it in perspective from an angle, I could get it to look like almost 180 degrees if I could figure out how to angle this properly. Okay. Your brain does this automatically. Your brain takes what you know to be a 90-degree angle and translates it for you. But I don't know, take a look at it around your room. A lot of the angles that I'm looking at in the corners of my room, I know are 90-degree angles, but very few of them look like 90 degrees if I were to just sketch them out on a screen right now. Here is Joe. So this triangle, DCB, is on the surface of the Earth. It's a horizontal triangle. This triangle, ACB, is coming up and out, and I'm sure that people could draw that better than I could. I'm not entirely sure this is that helpful, but it kind of gives me my strategy of working in this triangle using the sine law to find this side length, substituting that side length into this triangle, and then using a primary trig ratio to find that height. Okay. Important facts include the idea that we do not want to use the triangle ADB here. The triangle ADB is a diagonal triangle. It's on a diagonal surface, a diagonal plane. CDB is in a horizontal plane. ACB is in a vertical plane or surface. This is PLANE. The other fact is that this angle right here is not the sum of this angle plus that angle. Those two angles are not like side by side each other, next to each other in the same plane. One is in the horizontal plane, the other is in the vertical plane. You're not folding it down so that it's flat. Okay. Let's try the Emma on a bridge. Emma on a bridge. Emma is on a 50-meter high bridge and sees two anchors below. From her position, the Argo has a bearing of 230 degrees and the Blue Nose has a bearing of 120 degrees. Okay, I heard the 50 meters, but I didn't really see anything else vertical in there. So I think I'm going to do my bearings first. Now, the idea with the bearings, though, is that I would like to maybe imagine that Emma could take an elevator down onto the surface of the water, which I have no idea why I labeled Q. It might have been a typo. So here is the point below Emma. The Argo is at a bearing of 230 degrees. 230 degrees, bearings measured from north. Let's see, 230 degrees is going to be about 40 degrees short of west. So the Blue Nose is over there, 230 degrees. The Argo is, oh, sorry, no, that's the Argo. The Blue Nose is at a bearing of 120 degrees. 120 degrees. Blue Nose. Okay, this is my top-down view. Now I can use my side views, and I'm going to need two of them because Emma is actually, here, let's use this. Emma's like on the end of my pen cap here. She's up above here. Her bearing from there, she would still need to turn 230 degrees to see, say, the mast of the Argo, and she would need to turn 120 degrees to see the mast of the Blue Nose. But then she also needs to angle her head down to see them. You can see that from the side view. From one side view here, I'm going to look in this direction, and I'm going to see the Argo, the point below Emma, and then here's Emma up on a bridge. And I know Emma is on the 50-meter high bridge, and I know the angle of depression to the Argo to be 38 degrees. That's from the horizontal. She looks down 38 degrees. Quick parallel line theorem, and you can get that interior angle. Separate side view. Here's Emma on the bridge, the point on the water below Emma, and then the Blue Nose. Emma is 50 meters up, and Emma needs to look down 35 degrees. There's 35 degrees looking down. That means if Bob is on the Blue Nose, Bob would have to look up 35 degrees to see Emma on the top of the bridge. Side one, side two. Example number 2 is more complicated than example number 1 because you need 3 planes. You do not want to think of turning this image sideways and just having one big triangle. You would think these are the same side. Why didn't you just draw one big triangle like this? A lot of people do that, but then doesn't it look like the distance between the Argo and the Blue Nose is just going to be the distance from A to Q plus the distance from Q to B? Look at your top-down view to see why that's wrong. This distance from A to B is not this distance plus that distance. Okay. Let me just outline the strategy here. We were able to find, in a weird naming convention, I think I used lowercase a as the distance to the Argo. That's that distance right there. Notice AQ is part of both triangles. BQ is part of both triangles. Let's call that the distance for B. And I can solve using the tangent ratio. I can find A. Using the tangent ratio, I can find B. I then substitute that information into this triangle and just use the fact that angle AQB is going to be the difference in their bearings. 120 degrees, 110 degrees. So in my last step of work, I will have this side length, that's A, this side length, that's B, this angle, 110 degrees, and here's the distance in between the boats. I think I might have used Q. Okay, I'm set up to use the cosine law. There's my strategy. If you want to try a 3D diagram, you can see some of them on the lesson. I'll see if I could reproduce that for you now. If you're going to draw a 3D diagram here, though, you usually want to skew your perspective. So you make that north and you make that east. North and east are 90 degrees apart, but I'm looking at this through perspective. So here's Emma coming up out of the page. Here's the Argo down here on the surface of the water. Here's the blue nose over here. The problem is I haven't found many students that are able to communicate all of their work in just one diagram like this, because your angle of depression is actually like this angle here, which you then use your parallel line theorem to get that angle there. That's 38 degrees. This angle of depression is actually measured from that horizontal line. It's a real mess, actually. 35 degrees. There's the distance in between them. Take your time with it. Split your questions up into separate triangles. It doesn't need to be that difficult. Just go through a problem and identify horizontal information and vertical information and draw the two or the diagrams separately. Now, when you are working on your homework sheet, question number 1, Philip flying in a hot air balloon, is basically Emma on a bridge. Question 3, Simone looking through the tunnel, is a little bit like example number 1. Question 4 is like a more challenging Emma on a bridge. Question 2 looks easy and it's not hard to sketch. It is difficult to solve though. It's a challenging question outside of course level, I suppose. I'll be posting a solution for question number 2 on a separate video. Do your best and start by trying out the lesson examples.